Welcome to the Explainer. Today, we're diving into how to architect Laravel systems that degrade gracefully when third-party APIs inevitably go down. You know the drill, right? You build an integration, it works flawlessly in staging, and then it completely implodes in production. If you've been there, you're in exactly the right place.
Picture this. It's Tuesday, 2 a.m. Your code is absolutely pristine. Your tests, green across the board. But then, a third-party API you rely on just crashes, out of nowhere. Suddenly, your system throws a fit of 500 errors, critical user flows break, and you're jolted awake by a barrage of alerts.
So here's the crucial question we need to answer. When their API goes down, does your system actually behave, or does it just fail? Because look, the reality is we can't prevent external outages. They're just a fact of life in software. But we can completely control how our architecture responds to them. An outage isn't a failure of your code. It's really a failure to design for an inevitable reality.
Without a graceful degradation plan, an external outage creates this massive, lingering aftermath of a hard failure. We're talking errors users can't even act on. Your queue gets filled to the brim with chaotic retry jobs. Every single operation that touches that API just fails hard. And worst of all, there's no systematic way to recover those failed operations. You're just left manually cleaning up the wreckage the next morning, and nobody wants to do that.
Okay, moving right along to Section 1. The try-catch trap. Let's see how the most common developer instinct actually creates long-term technical debt.
So your immediate instinct is probably to slap a call site try-catch block right where the API is called. I mean, we've all done it. But honestly, this is a trap. It forces you to make a rushed fallback decision right in the middle of writing completely unrelated code, and that leads to wildly inconsistent behavior across your app. Often, we just end up logging the error and giving up. Instead, using an explicit model trait to handle this fallback logic creates a predictable, ironclad contract for your entire application. It's a total game changer.
Which brings us to our next section, a business decision in code. This represents a fundamental shift in mindset, moving us away from just technical patching and toward actual business logic.
There's a quote here that says, "The fallback decision is a business rule, not a technical setting." And I think this brilliantly hits the nail on the head. Deciding whether your system should fail loudly or continue silently when an API goes down isn't just about catching exceptions. It's a fundamental business question. Is the primary operation still valid without this third-party integration?
To answer that, we can add a very explicitly named method to our eloquent models, shouldContinueWithoutSync. Notice the phrasing there. It doesn't sound like you're just, sweeping an error under the rug. It documents exactly what happens when the endpoint is unreachable, right inside your business logic. It literally asks, hey, can this record exist locally before the external system even knows about it?
When you implement this, the default behavior should always be fail loud. Why? Because failing loud surfaces problems immediately. If you default to failing silently, every model that hasn't specifically considered an outage will just eat those errors quietly, completely hiding massive system failures. So by defaulting to fail loud, we force developers to consciously opt in to fail silent mode. They literally have to stop and think about the business consequences first.
Okay, let's pivot and talk about handling the actual HTTP calls. To prevent your workers from stalling for like 75 seconds or more waiting for a default OS timeout, you absolutely must set two specific timeouts explicitly on your client. First, connectTimeout. This limits how long to wait for the initial TCP handshake, which catches unresponsive hosts. Second is the standard timeout, which limits the total request duration. This one is crucial because it catches servers that accept a connection, but then just sort of stall midway through. Setting both of these prevents two very distinct major failure modes that will otherwise completely block your workers.
Also, a really quick but critical security warning. Never use without verifying on public APIs. I mean it. You might see this floating around in some older legacy codebases, but it belongs strictly on internal private networks. Disabling SSL verification on public APIs costs you nothing to keep on, but turning it off invites massive threats like man-in-the-middle attacks and DNS hijacking. So yeah, just don't do it.
Now, before we look at data recovery, this is a vital debugging step you really can't skip. It's the traceability key. Getting that request ID from the context. Think about it for a second. Asking a third-party team, hey, can you check request ID A3F2C1 takes them maybe 3 seconds. But saying, it was a post request around 2:30 p.m. guarantees you are going to be digging through logs all afternoon.
Passing a request ID in your outgoing headers costs nothing during normal operations, but it is literally invaluable for tracing failures across systems instantly.
All right, moving into our next section, building the recovery path. Because handling the failure moment gracefully, well, that's really only half the battle. Now we actually need to recover that unsynced data. When a model is created locally because their API was down, you now have data in your system that the external system is completely clueless about. To fix this, you need to implement 2 specific steps. Step 1, queue a delayed retry. Step 2, set up scheduled reconciliation. If you skip this, it's not just a temporary glitch, it means permanent data inconsistency between your app and the third party.
So how do these recovery strategies actually compare? Well, delayed retries handle the failure immediately. By adding a delay, you prevent your system from just hammering a down server over and over. But scheduled reconciliations, those act as your nightly safety net. If an outage is super prolonged and your delayed retries eventually exhaust themselves and fail, the scheduled job sweeps through and catches anything that's still unsynced. You really want to use both to make your app bulletproof.
Next up is a section I love, the senior engineer question. Let's tackle that one specific edge case that veteran architects always ask about when implementing this fallback pattern.
And it's a really fascinating question. What if the local write fails after the external API already succeeded? We've talked about what happens when their API is down, sure. But what if it's up, the request succeeds, but then your own local database write fails? This introduces data inconsistency in the exact opposite direction. The external API has the record, but your local database doesn't. No way!
To safely fix this and build a complete reliability solution, you absolutely need a 2-part approach. First, wrap those local writes in database transactions so they can roll back cleanly if something breaks. Second, send an idempotency key with the external API call. Think of this key as a unique stamp for your request. It ensures that when your system inevitably retries the operation, the third party recognizes that stamp and doesn't accidentally charge the user twice or create a duplicate record on their end.
Okay, final section, before you ship. Let's bring this whole shebang together into a practical framework so you are fully prepared for your next production deployment.
Seriously, I highly recommend taking a quick screenshot of this production readiness checklist. Before you ship, verify that your connectTimeout and standard timeout are set explicitly. Double-check that there's no without verifying flags on any public APIs. Ensure you've made explicit shouldContinueWithoutSync decisions. Make sure those fail-silent models actually have recovery paths built out. Pass that request ID in all your headers, and use idempotency keys wherever the external API supports them. Doing this creates a consistent baseline that stops minor outages from becoming full-blown disasters.
So the 2 a.m. outage is inevitable. Do you actually have a plan? Look, the next third-party outage isn't a possibility, it's a guarantee. But by applying these architectural patterns, you won't be scrambling under pressure in the middle of the night. You'll just let your code smoothly handle the fallback, allowing you to finally get some sleep. Thanks for joining me on this explainer. I'll leave you with this. Look at your most critical integrations right now. If that API drops in the next 5 minutes, does your system gracefully degrade, or does it drag your entire application down with it?